You know when you're using an app and it's just crazy fast? You hit search and boom, less than a second later, it's found the one thing you wanted out of millions, maybe even billions of items. It seriously feels like magic. But here's the thing, it's not magic at all. It's just some really, really brilliant engineering. And today, we're going to pull back that curtain and see exactly how they do it.
So how does it really work? How can a system wade through this massive ocean of data and just pluck out that one specific record? Your email, your photo, your order, almost instantly. That's the exact question we're going to answer right now.
All right, so to get our heads around this, the very first thing we need to grasp is a fundamental concept. What we see on our screens is almost never what the computer is actually doing in the background. There's a big difference.
On the left, you've got the logical view. It's clean, it's organized, right? Think of a perfect spreadsheet with neat little rows and columns. That's the version made for us humans. And then, on the right, that's the physical storage. That's the reality on the hard drive, a way more complex system of files and blocks and bytes that the machine has to deal with.
So that logical file is simply our perspective. When you look at, say, a student database, you see a nice, clean table with columns like roll number, name, and marks. It's all designed to make sense to us, not necessarily to be the most efficient way to slap data onto a disk.
The physical file, on the other hand, well, that's the machine's reality. Data isn't stored one perfect row at a time. Nope. It's all grouped into these fixed-sized chunks, usually called blocks or pages. A single one of these blocks might hold dozens, maybe even hundreds of records all jumbled together. And that difference is really at the heart of the whole challenge. Okay, so we've established that data is physically stored in these big chunks. The next logical question is, how on earth do we organize it all? Because if you don't have a system, you just have digital chaos. And that's really the crucial point. If you just add data as it comes in, you end up with a massive unordered pile. Trying to find one specific piece of information would mean you'd have to scan the entire file from start to finish. For a big database, we're not talking seconds. That could take minutes, hours, maybe even days. The simplest way to handle this is something called heap file organization. And simple is definitely the key word. As new records come in, they're just tacked onto the very end of the file. Super fast for adding new data, but like we just said, absolutely terrible for finding it later. The perfect analogy for a heap file is just tossing student admission forms into a big folder as they sign up. Now, say you want to find one specific student. Well, you've got to flip through every single form from the top until you find the one you're looking for. Not exactly efficient, is it? So, naturally, the next step is to bring some order to that chaos. With sequential file organization, records are stored in a sorted order based on some kind of key, like a student ID. This makes searching way, way faster, especially if you're looking for a range of things. Think of a library bookshelf, all sorted perfectly by book number. Finding book number 150 is easy, right? You know it's going to be after 149 and before 151. But here's the catch. What happens when a new book, let's say number 50, shows up? You have to literally shift every single book after it just to make room. So adding and deleting things becomes a very slow, painful process. This brings us to a much, much cleverer approach, hash file organization. Here, a special math function, a hash function, takes a key, like an employee ID, and it instantly calculates the exact address on the disk where that record should live. There's no searching involved at all. You just jump. And the analogy here is just perfect. Imagine school lockers. If every student's locker number is their ID number, and your ID is 103, you go directly to locker 103. You don't have to check every other locker to find yours. It's direct, it's instant, and it's incredibly fast for finding an exact match. So we've got a few pretty good strategies. But what happens at a massive scale? You know, when you're dealing with billions of records, even these methods can start to show their limits. So is there an even more powerful shortcut? One that kind of combines the best of all worlds? Well, the answer is a big yes. And that ultimate shortcut is called indexing. This is the technique that truly unlocks the incredible speed of modern databases. It is the secret sauce behind that magical split-second search we were talking about. Here it is. This is the big aha moment. With indexing, the database completely stops searching through the massive data file itself. Instead, it searches a much smaller file, the index, which basically acts as a map, telling the system exactly where to find the data it's looking for. The process is just brilliantly simple.
First, the database searches that tiny index file for your key. The index entry gives it a pointer, which is really just the physical address of the full record. Then, it uses that pointer to jump directly to the right spot in the massive data file and grab what it needs. It's just like using the index at the back of a textbook to find a specific topic, instead of being forced to read the whole book from cover to cover. But of course, it's not quite that simple. There are different kinds of indexes, and each one has its own strengths and weaknesses. The two main types you'll hear about are dense and sparse indexes, and choosing between them involves some really important trade-offs. A dense index is the most straightforward type. It creates a map entry in the index file for every single record in your main data table. This is incredibly thorough, and it makes searching extremely fast because there's a direct pointer for absolutely everything. The perfect modern analogy is an online library catalog. You can type in the name of any book, and the system instantly tells you its exact shelf location. Every single book has its own entry. It's comprehensive, and it is lightning fast. Now, a sparse index takes a totally different approach. Instead of creating an index entry for every single record, it only creates one for certain records. Usually, it's for the first record in each data block. This means the index file itself is much, much smaller. This is where that classic phone book analogy works perfectly. The top of the page tells you the first name on that page, right? Let's say Smith. To find Smith John, you use that header to jump to the right page, and then you do a quick scan of that one page to find him. So the index gets you to the right neighborhood, and then you just have to do a small, quick search. So the crucial thing to understand here is the trade-offs. This table lays it all out. A dense index is faster for searching, but it eats up more storage space, and it's more work to maintain whenever you add or delete data. A sparse index, on the other hand, is smaller and easier to maintain, but it's a little bit slower for searches, and importantly, it requires your data to be sorted first. And that brings us to the most important takeaway from all of this. The incredible speed of modern databases isn't about finding one single best solution that works for everything. It's about engineers making a series of smart, deliberate trade-offs, balancing speed against storage and efficiency against maintenance. It's not magic, it's a masterpiece of logical design, which really leaves us with the real question. Which trade-off is the right one for your data?